Hello everyone. This is the first of two lectures in which we discuss semi-local and non-local exchange correlation functionals. What we will do is look at exchange correlation functionals that go beyond the local density approximation, LDA, and the generalized gradient approximations, GGA. In this lecture, I will specifically concentrate on the so-called meta-GGA. I will explain what it is and how well it performs. The concept of meta-GGAs, like many other important concepts in DFT, comes from John Perdue, whose picture you can see here. So let's begin by talking about what we mean by local, semi-local, and non-local. The picture illustrates some electronic density distribution. We want to consider approximations for the exchange correlation energy EXC for this system, which we write as an integral over the exchange correlation energy density, little epsilon xc of R. Now, a local exchange correlation functional would mean that the exchange correlation energy density at point R depends only on the density at the same point R, so we only need local information to construct epsilon xc. In a semi-local functional, on the other hand, the exchange correlation energy density depends on the density and/or the orbitals at point R, as well as their gradients at point R. So we need information in some small neighborhood around R to construct the functional. Finally, in a non-local functional, the exchange correlation energy density at point R depends on the density or the orbitals everywhere throughout the system, not just at point R. Now let us consider the ladder of approximation in DFT, which we had already seen in an earlier lecture. You find the LDA on the lowest rung, then GGA, meta-GGA, hybrids, and RPA-like functionals. As the name suggests, the local density approximation LDA is a local functional. GGA and meta-GGA are both semi-local functionals, as we will discuss further below. Finally, hybrids and RPA-like functionals are fully non-local. Let us now take a look at the generalized gradient approximations, or GGAs. Here, the exchange correlation energy is written as an integral over a function that depends both on n sigma and the gradients of n sigma, where n sigma of R are the spin densities for sigma equals spin up or spin down. The spin density is, of course, a sum over the squares of the occupied cone-sham spin orbitals. The best known examples of GGAs are the BLYP, which stands for Becker-Li-Yang par, dating back to 1988, and PBE, which stands for Perdue-Berg-Ernzerhof, dating back to 1996. Let us now come to meta-GGAs. Here, the exchange correlation energy is written as a functional of the spin densities, their gradients, as well as tau sigma, where tau sigma of R are the kinetic energy densities for spin sigma. As you can see, tau sigma is constructed as the sum of the gradients of the cone-sham spin orbitals squared. Well-known examples of meta-GGAs are TPSS, which stands for Tau, Perdue, Staroverov, and Scuderia from 2003, and the recent SCAN functional. Here, SCAN stands for strongly constrained and appropriately normed, which was proposed by Sun, Brzezinski, and Perdue in 2016. Let us now take a closer look at the meta-GGAs. The main question to ask is, why should it make sense to include the kinetic energy density as a quantity for constructing the exchange correlation energy? It turns out that tau of R is quite sensitive to the degree of localization of electrons. It therefore helps the functional to better distinguish covalent single bonds and metallic bonds. Furthermore, tau of r incorporates exact constraints of 1 and 2 electron densities. Now, an important property of the kinetic energy density is that it is an implicit density functional. Tau of r depends on the gradients of the cone-sham orbitals, and this means that we cannot write it as an explicit functional of the density. Of course, the Hohenberg-Kohn theorem tells us that tau of r must be a density functional since the cone-sham orbitals depend on the density. But this density dependence is only implicit through the cone-sham equation. The functional itself is a semi-local orbital functional because it depends on the local gradients of the orbitals. As a density functional, on the other hand, it is non-local. Let us now discuss two examples that compare the performance of GGA and meta-GGA. The first example is a study where the formation enthalpy of a number of solids was calculated. The solids are simple binary compounds made up of main group elements. The view graph compares experimental results versus theory. If theory and experiment agree, then the data point for the respective compound lies on the diagonal. As you can see, the data points for the scan meta-GGA, the red squares, are much closer to the diagonal than those of PBE, the circles. The insight shows that the mean absolute error of PBE is 0.293 electron volts per atom, and for scan it is 0.038 eV per atom. The study also showed that the results were less accurate for transition metal compounds, but still quite good. The second example involves structures formed by 6 water molecules. Such structures are important in the formation of ice. You can see that SCAN, the green dots, compares very well with CCSDT, which is a high-level, very expensive quantum chemistry method, and predicts the correct energetic ordering of the 4 water hexamers. This is in contrast with PBE. The PBE hybrid PBE0, which we will discuss in more detail in the next lecture, is not doing much better, even with a van der Waals correction. See the purple squares. We conclude from this that the SCAN meta-GGA can correctly describe short to medium range van der Waals interactions. Let me now come to the main messages of this lecture. We have been looking here at non-empirical exchange correlation functionals, which are constructed so as to satisfy certain known exact constraints and conditions. The more conditions are satisfied, the more accurate the functional is. We have seen that GGAs and meta-GGAs provide us with reliable accuracy and can predict the properties of materials efficiently. When will it be okay to use semi-local functionals in DFT? This depends, of course, strongly on the system and the material, but in general, whenever the exchange correlation hole is sufficiently localized. On the other hand, when do semi-local functionals fail? This may happen for weakly bonded systems where long-range van der Waals forces are important, also for strongly correlated systems, and, of course, for the case of band gap calculations. So, stay tuned for further discussion of semi-local and non-local functionals.